Hey everyone, I'm Pranav, this is Daniel, and our project is the Reddit Classifier. So as we all know, Reddit is an online platform that subdivides into smaller subgroups called subreddits. And each subreddit has a moderator, and one of their jobs is to identify and remove off-topic posts. This is a very manual and repetitive process, and there's a lot of room for errors, and moderators also don't always have time to actually tell a poster where their post actually does belong. And so we believe that natural language processing offers us a smarter way to analyze the contents of a post and predict where it actually does belong. So for this, we need a lot of data. So we picked 20 subreddits and took 50,000 posts from each one and ensured that each post that we collected had at least 50 net upvotes. This ensures it's a good example of what actually belongs in that subreddit. And we also only ended up using the titles of each post because we believe it's a sufficient indicator of the actual contents of the post, and it drastically reduces the resource requirements to build a very big data set. At this point, it's worth noting that a limitation of our current approach with a classification approach is that it's not very generalizable more out of the 20 subreddits we actually pick. To actually convert our titles into a form our network understands, we do this in two ways, with word embeddings and character embeddings. We did not use any pre-trained embedding models because we believe that Reddit has a very unique vocabulary that might get missed out on. So with word embeddings, we take our sentence, we strip it down to bare bone words, turn it all lowercase, and assign every word that occurs more than 100 times in our corpus with a unique integer, and the rest of the words get a -1 value. For character embeddings, we split it by character, replace all non-ASCII characters with -1, each character gets a unique integer, and we pad it all to the longest title length in our data set. A quick justification for why we choose to ignore words that occur less than 100 times. So the words that we ignore are here in orange. And notice that while they make up a very big chunk of our vocabulary, they're actually a minority when it comes to actually being used in our corpus. So it's a safe assumption that they're not very prevalent or relevant to the decision-making process, and we can kind of ignore them in our search for main keywords. So now Daniel's going to go over how we actually use this to train our model.
All right, so we tried out different models to see which one works. So we tried both character and word embeddings. In the end, the character embedding model with 18-layer ResNet performed the best. So we created this one on our own, reading some literature. Essentially, the easiest way to visualize this is to imagine an 18-layer convolutional neural network. Last couple layers are fully connected with a couple caveats. So basically, the main catch is you have a number of blocks. Each block is 2 convolutional layers. And then in between the blocks, you have these shortcuts called residuals. And in between the shortcuts, you add the output between like block 1 and block 2 together and so forth. And the idea here is that you create a shortcut which the gradient can learn through and help you learn deeper layers more efficiently. The other catch is that as you go downstream in blocks, the channel size increases. So you have like bigger and bigger channels, and the width decreases as you have smaller and smaller sentences in length. So the way you deal with that is you have residual convolution on even number of residuals. This essentially is a linear layer, and then that increases the width. Sorry, that increases the channel size, and then you decrease the width by performing addition with a stride of 2. And these are the results. So the baseline works 77% accurate. On the test results, the word embedding was 78%, and the character embedding was 79%. There's some overfitting going on, nothing too crazy, but 82% versus 79%. Loss looks pretty clean, so we probably picked the right learning rate that we used. Here's some qualitative results. So this is a confusion matrix. As you can see, the diagonal is pretty clean. There are some caveats that we're going to discuss when we look at the precision slide. Basically, the best performing subreddits are the sports ones, as well as Today I Learned and Earth Porn. And then the worst performing subreddits is AskReddit and AskMen that get confused with each other. So here's the precision by subreddit. Like I discussed, Today I Learned and Earth Porn are the best ones. There's a pretty simple reason. Today I Learned has a tag called TIL before any post, and Earth Porn at the end has original content or reproduced content at the end that they tag with in the post, so they want to pick that up pretty well. Then the sports ones have very specific terminology, and then at the lower end you have AskMen being confused with AskReddit, and as well as the political subreddits will have different leanings, generally talk about the same thing, so the accuracy is not as high for them. So what do we learn from this? So essentially the main factor is that character embeddings outperform word embeddings in analyzing text data. So why exactly is that the case? Well, generally speaking, these words that we discussed are actually important, as it turns out. The idea basically is that you have these rare occurring words that sometimes have very important concepts to talk about. And while we can't pick them up on their own, we could learn about the root words of them and capture them well to help the character model work well. Additionally, we look at grammar, special characters, capitals, etc., and that also helps the model perform more accurately, as there's important patterns in each one unique to subreddits. A good one is also why did CNNs perform RNNs? There's a lot of reasons for this. Sometimes RNNs are better, sometimes CNNs are better for text posts. I think the main reason here is that these titles are fixed in size, only up to 300 characters, so the CNNs can learn a lot of patterns without losing the ability to work with very different sentence sizes. And we acknowledge that there's some limitations to this approach. So is supervised learning inherently limited? In this case, I would say yes, at least in the way we did it. So there's only 20 subreddits that we looked at, but there's tens of thousands of subreddits that we can't have a massive classifier for. So perhaps in the future, we can either take some kind of unsupervised approach or do some binary classifier. And if you're past a certain threshold, you're flagged for not belonging to that subreddit. And overall, these results are pretty promising, but we can also extend it by looking at more data from an individual subreddit. So we can look at more than just the initial title. We can look at the body of the post, as well as the associated pictures or potential links of where the post comes from. For example, if it's a Twitter post or et cetera, where it comes from, maybe that can make them a lot more accurate.
All right, thank you. Interesting. A bunch of engineering going on here. On the embeddings, the word embeddings are simply integers representing the number, right? Is that correct?
What's the next one?
This one? Yeah.
The word number is just a single number?
Yeah, so that's how we pre-process it. So we turn text into a string of integers. But then
But one word is one integer.
one unique word is one unique integer.
So there's no meaning behind that. It's just
A way to convert the, it's like basically a pre-processing we do, and then when we load them into Torch, you just, it's like a one-hot you do, essentially. Or it's not a one-hot, it's, it maps it to an embedding.
To what embedding?
So like, basically imagine we have 10,000 words, right? So we have a matrix in the embedding layer that's 10,000 by 100 size. And then each column has a unique number. So that this number is mapped to the column.
But I thought you said you couldn't use pre-trained.
Yeah, we train our own embeddings.
You didn't talk about that part.
Yeah, so we train our own embeddings as part of the overall learning. We didn't do a separate model. We just fed them in and the model learned them on their own, just because we had a very large corpus of our actual supervised data. Like our corpus is like 10 million words, so.
But that was in a separate process.
No, same one. So I'll show you. So this one, in the word embedding, it's not a convolutional layer, it's an RNN. But your first layer is an embedding with a learning rate, so you can learn through it. And the idea is that if you have a lot of words in your supervised learning, you can very efficiently capture the vocabulary without the need to have a word to vec or a glove. You just learn it directly on the model.
Oh, that's interesting. Okay.
Yeah, the only reason it works is we have a really large corpus size. So we have 1 million titles, which is about 10 to 15 million words.
In the character embedding, you went by it.
Yeah, sure. So character embedding is a similar idea. So what you do here is that you have a unique number for each character, and you basically map all the ASCII characters to a unique number. And then you basically feed these raw characters into the model, and it picks up words on its own. It only works when you go super, super deep, as we learned out. Like when you're doing a 5-layer convolution, it actually completely bodies against the baseline. The baseline outperforms it really well. But when you go to these 18-layer, really fat models, the character embeddings start outperforming the word embeddings.
Interesting. Mike?
I have a couple comments. So you padded the vectors with ones, or minus ones, sorry, and then you also made missing characters a -1. So what was the reason for that? Why didn't you use 2 separate characters or symbols? One for this is just extra padding, and one for this is missing. Do you think there's anything useful the model could have learned from making that decision?
Let's go to that.
So this one doesn't have any -1s, but it could have, right?
Yeah, so this one in general, we actually had a unique character for, so -1s weren't necessarily padded with it.
Oh, okay.
Yeah, I guess just a syntax error we posted here. On the word embeddings, you're definitely right. Maybe having a different one would have worked out. But actually, no, it wouldn't have. I take that back. Because we take the final layer. We don't learn it all the way through. We have a stop, and at the stop, we extract the value for the final output.
Oh, okay. Oh, so you have a stop. Okay.
Yeah. So basically, because it's an RNN, that was the best one for the word embedding. So you take out the last value and you use it. Perhaps that might have made the CNN a little better for the word embeddings, but to be honest, CNN was pretty garbage in the word embeddings anyway. So
Sure.
I doubt it would have outperformed the RNN.
So 2 more comments. One of them saying, so you did best on Today I Learned, likely because TIL
Yeah.
appears at the beginning of them. So if I post that in another subreddit, I'm not going to put TIL in that. So your model's not going to tell me to go put it in TIL. right?
Yeah, probably true, to be honest. Especially with TIL, where you have like this overfitting, I guess, going on, where you have like TL is like 100% likeliness. If there's TIL, it belongs to TIL.
And my third point is your loss functions. Could you go to the plot with all
Yeah,
of them?
sure.
So the micro bumps that are occurring are almost identical across train, test, and validation, which means that your model's parameters are changing, and the reaction to those changing parameters is almost the same for all your data sets. Why do you think that is? That's kind of weird, because you'd imagine that if you're doing slightly different batching and they're different values, then it wouldn't get exactly the same losses on all three sets. It just looks a little suspect to see them all so very similar, especially validation and test, like almost identically following each other.
Yeah, to be honest, we don't have a simple answer to it. I think the most likely case what's going on is that usually you have little bumps when you have small test validation data. Here you have pretty large test and validation data, so like these bumps are showing something deeper than just randomness. If I had to guess what it is, you would have several batches that might have several really sensitive parameters that completely jump up the result. And especially when you have these really deep models, like you're very prone to like one sensitive thing either being batch normed a little differently that one run, or a very late parameter like increasing magnitude a lot due to not having a small enough learning rate. You know, this is Atom, so sometimes the learning rates are different size.
Yeah.
So some small thing could basically, for an epoch, throw off an entire accuracy for a little bit.
Yeah, it's interesting. It's almost like they're all representative enough to show the same
Yeah, yeah. I
change
mean,
in the
even
model.
like, so we have, what is it? We have 1 million training results. So we have 900,000 training results and 50,000 validation and 50,000 tests. So like, I would say they're fairly representative of the data set, even on their own.
One quick comment, just when you're showing what you called qualitative data, you showed a confusion matrix. And what I mean by qualitative data is you actually show an example and say this one here's one that was correct, here's one that wasn't, and maybe speculate as to why. It's not, this is quantitative in my view. So.
Yeah, we'll probably include in the final report then.
Yeah.
Right.
We'll include the.
Yeah. Please do. And it's always useful to look and see what it's actually doing, and speculation can help in this world. Great. Any comments or questions? Let's keep that record clean today. All right. Thank you.